Welcome back. Today, we're going to begin to learn about how chemical bonds form. We'll apply our knowledge of electronic configurations to look at ionic compounds, which result from the sharing of electrons between ions. By the end of this lesson, you should be able to understand this sentence from Linus Pauling's Nature of the Chemical Bond. The most important electrostatic bond is the ionic bond, resulting from the Coulomb attraction of the excess electric charges of oppositely charged ions. The atoms of metallic elements lose their outer electrons easily, whereas those of non-metallic elements tend to add additional electrons. In this way, stable cations and anions may be formed, which may essentially retain their electronic structures as they approach one another to form a stable molecule or a crystal. I'll also be teaching you about how to name ionic compounds. We've learned a little bit of this already. And we'll specifically look at variable charge ions, metals that can have a variety of different charges. We'll look at some transition metal ions and their electronic configurations. And lastly, we'll end with Coulomb's law, which is how to calculate the energy of an ionic compound when it forms. This is the material from chapter 5.12 and chapter 6. To begin with, let's look at some simple ionic compounds and how we can picture the electron transfer that's occurring. Well, to begin with, ionic compounds form between metals and nonmetals. So when you're looking at the periodic table, the metals are everything to the left of this black staircase, and anything to the right of that is a nonmetal, including hydrogen. There are a few elements that are metalloids, which can have both metallic and non-metallic properties. And depending on the compound, they may be considered a metal or a nonmetal. Metals, as we saw, have low ionization energies. Therefore, it's easy to remove electrons to form a positively charged cation. Nonmetals, on the other hand, have higher higher ionization energies, but they also have this property called an electron affinity. An electron affinity is the opposite of an ionization energy. It's the energy that's required to gain an electron. And they typically have high electron affinities, therefore they readily gain an electron to form a negatively charged anion. We'll take a look at some electron affinities later on in this chapter. In an ionic bond, electrons are transferred from the metal to the nonmetal. We don't draw a line between the symbols when we write an ionic compound because those are reserved for covalent compounds where there's a sharing of electrons. To remind you of what a first ionization energy equation looks like, we have some metal with the symbol X, and we apply an energy, and as a result, we get a positively charged cation and an electron that's emitted. And then if we were to go and remove another electron, we would start with that cation and remove one more electron. The electron affinity equation is the opposite, where we start with a neutral atom and add an electron to form a negatively charged anion. And we can do that multiple times. And we call those second and third electron affinities. Let's look at the ionic compound that results when we have magnesium and oxygen that come together. Now, magnesium is in the second group of the periodic table, just below beryllium. We'll be making use of this other chart today. It's the periodic chart of the ions. And to begin with, we'll look at magnesium and see that it has a 2+ charge. That is, the most stable ion of magnesium has a 2+ charge, as does everything else in the second group. So the most stable cation of magnesium is Mg2+. Oxygen is in the 16th group, or group 6A, and its most stable anion is O2 minus. So it tends to gain 2 electrons. The compound that results from magnesium and oxygen coming together is MgO. And how do we get that result? Well, we can look at the Lewis dot structures for magnesium ion and oxygen ion. And to begin with, let's look at the neutral magnesium, which has 2 valence electrons. And then oxygen, which has 6 valence electrons, which we draw like this. Okay. When magnesium goes to combine with oxygen, it's going to donate 2 of its electrons. So what will occur is 1 electron will go to fill the orbital here, and this dot will go to fill the orbital here. When I say the orbital, I'm referring to the 2p orbitals that are unfilled on oxygen. And as a result, we get a doubly positive charged magnesium, a 2 plus magnesium ion, and we get a 2 minus oxygen anion. So in red, I will draw those dots those electrons that got transferred. Okay, so this is what you would draw for an electron transfer equation for magnesium and oxygen combining to form magnesium oxide, which is how we're going to name this compound. Another way we can represent this is using the electronic configurations that we've learned. If we go back and look at our atomic orbital handout, magnesium is the 12th element, so it's going to have 12 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the electronic configuration would then be using the short notation, neon 3s2. So magnesium has the electronic configuration of neon as its core electrons, and then its valence electrons are in the 3s2. When oxygen is combined, so oxygen has, let me just look it up. It has 8 electrons, and what we're going to do here, I need to erase a couple of these. It's not letting me erase. There it is. So we have to put 3 electrons up first, and then we put 1 electron down. So the electronic configuration of oxygen is the same core as helium. That would represent the 1s2, and then 2s2, 2p4. During the electron transfer process, the 2 electrons that are the valence of magnesium go to oxygen, and we can see very easily why this might occur. So magnesium 2 plus will end up as the same configuration as neon, and oxygen 2 minus will end up with the same configuration of neon as well. That is, neon has helium 2s2, 2p6. I think maybe we can write it like that. Let's do that. Helium 2s2, 2p6, or we could write neon. So here we can see that whenever an ionic compound forms, there's going to be the completion of a outer shell or the removal of all the electrons from the outer shell. This isn't always going to occur. There's always going to be some cases where you'll want to, instead of doing that, we'll half fill the orbitals. And we'll get to that though. So let's look at another example where calcium and chlorine combine together. Calcium is also in the second group of the periodic table. It's below magnesium. So we would suspect, based off its electronic configuration, that it would also form a 2+ charge because it's going to want to lose those 2 electrons. And chlorine usually forms the chloride anion, which is Cl-. That's in the 17th group, so it's only one electron away from having a noble gas configuration. Now, what is the compound that results here? Well, let's start by doing the same approach that we just did. We'll have calcium with its 2 valence electrons, and then chlorine with its 7 valence electrons. Again, you can put these dots kind of anywhere. I'm doing it this way so you can easily see where these electrons go. Now, when we go to form this compound, we note that we can only get rid of one of the electrons for calcium. So in this, to resolve this, we actually need a second chlorine atom for every calcium atom. And then we can get rid of that other electron, and it will go here. And will result in getting calcium chloride, which has the formula of CaCl2. Sorry. Okay. Now, we can write this a couple different ways. I like to put calcium in the middle and then one chloride anion on either side of it. Oh, that's carbon. We need to add an L. There we go. And add a negative charge. And just to make it clear, there is one electron transferred to each of these. Oh boy. Let's fill that in. There we go. We can again write the electronic configuration transfer equation, which I liked writing these. These are good practice. So calcium is below magnesium on the periodic table. And it's not going to have a 3s2 electron. It's going to have a 4s2 electron. Now we can also look and see calcium's in the 4th period. So it's going to start with the 4s subshell. On our atomic orbital handout, which you can find on Canvas, you could have this available to you and see 1s2, 2s2, 3s2, 4s. There we go. This is where calcium is. So calcium has the noble gas configuration of argon, 4s2, and chlorine has the configuration of neon, 3s2, 3p5. All right, so that's good to practice that. And then when these combine together, one of these electrons goes to this chlorine, and then the other goes to a different chlorine. So we're going to actually have to write a 2 here. So we're kind of balancing this equation, and then we'll end up with calcium having the noble gas configuration of argon, and it's 2+ charge. And then we have a compound that results here. So calcium chloride. Not quite sure the best way to write this, but each of these chlorines here are going to have the configuration that matches argon as well. I'll just do this shorthand, and we'll write it like that. A lot of times we're not going to write the negative charge here in the compound name. We actually never write it, but it's implied that in an ionic compound, when I write calcium chloride like this, CaCl2, that the calcium has a 2+ charge and the chlorines have a -1 charge. There's one more example of this, but I think you get the idea. So I'm going to skip this example. Now, the chemical formula is going to be the simplest electrically neutral set of ions, meaning for the previous example, we have 1 calcium and 2 chlorines. Another way we could write this is 2 calciums and 4 chlorines. However, that's not the simplest set. We want to make sure that there's no common factors other than 1 in these integer values here. One thing that's pretty interesting about ionic compounds is they don't just exist as these ions floating independently. They're actually arranged in a 3-dimensional crystal lattice. And one way of visualizing that is through this image here, where we have a sodium chloride crystal, which is composed of 1 sodium ion for every chloride ion. And the smaller element here is the sodium ion. And then the larger ion here is the chloride anion. And we'll talk about why the anions are much larger than the cations in just a little bit. Due to this arrangement, ionic compounds are always going to form crystalline solids. And they always will have high melting points and take a lot of energy to break. So ionic compounds are generally referred to as salts for their similarities to sodium chloride. Well, not all of them, but many of them are. And a couple are potassium nitrate and magnesium sulfate and calcium carbonate. These compounds will all form like these powders that we can see in real life. But we'll learn a little bit why the energy here is so much for a crystalline solid. But I want to finish up the last part of chapter 5, which is about atomic radius or atomic radii, which are the sizes of the atoms from the nucleus to approximately where the outermost valence electrons are. Because an atom isn't like a rigid object, the radii of a set of atoms is going to be a little bit arbitrary in how we define where the edge of that atom is. Oftentimes it's done using crystallographic data, which gives us an approximation of what the radius is. So I pulled up some of that crystallographic data here for the periodic table. And if we take a look at all the different radii, we see that the smallest one is helium with a radius of 0.28 angstroms. An angstrom is a non-SI unit that stands for 10 to the negative 10 meters. And the next smallest element is hydrogen. As we look at lithium and then beryllium, then boron and carbon and so on, as we go right on the periodic table, the radius decreases in each period or in each row. But as we go to the next row of the periodic table, there's a jump. And that jump corresponds to the filling of another shell, another orbital that's located further from the nucleus. So that part makes sense based off of the electronic configurations of sodium versus lithium. So sodium has a 3s orbital that's filled in its ground state, whereas lithium only has a 2s orbital that's filled in its ground state. All right, so the largest element is going to be francium on the periodic table, which is located in the bottom left. And the lanthanides, they fit in here, and the actinides fit in here. And then we don't have experimental evidence for the elements greater than, I believe that's californium. No, Cm is curium. So we don't have crystallographic data for berkelium or any of these other transuranium elements because there's just not enough atoms to measure it. And then another way of looking at this data is where we plot the atomic number against the radius in picometers. So rather than angstroms, we could look at picometers instead, which is 10 to the negative 12 meters. We can see that periodic trend where the largest elements are your alkali metals, lithium, sodium, potassium, rubidium, and your smallest radii are going to be your halogens or your noble gases. So the noble gases aren't included on this data, and that's probably because noble gases are difficult to get crystallographic data for. So perhaps these values were estimated. But nonetheless, we can still see that trend where it drops very consistently. But there are some regions where we have these kind of flat lines. These are our transition elements. And in these regions, the trend isn't as obvious. And sometimes it breaks the trend where it goes up. And that's just something to keep in mind, that this isn't a definite explanation. And then once you get to the lanthanide elements, we can see they fit in here. And this results in the transition metals right here of the 5D block being similar in radius to the 4D block. So they're not as large as you might expect. Now, why is the radius decreasing as we go to the right on the periodic table? Well, one of the reasons that I've learned is that as we increase the number of protons on an element, we increase the effective nuclear charge of that element. So the more protons, the larger positive charge in the nucleus. And as we add more and more electrons, they just get further and further attracted towards the radius. So they just essentially get pulled in towards the nucleus more and more. So as we go from lithium to beryllium, beryllium has 4 protons, and so it's going to have a larger pull on those electrons. But as we look down the periodic table, the nuclear charge is still increasing. So as we get to sodium, so why is sodium larger? Well, that's because the outermost electrons begin a new shell, and those new shells are a lot further from the nucleus. So this effect outweighs the increased nuclear attraction. And I think it's also important that we understand what the atomic radii of ions are. And when an electron is more attracted to the nucleus, we say that the atomic radius is smaller. So what happens when we remove an electron from an element? So if I have a sodium atom, which has 11 protons, 11 electrons, and I remove an electron, well, that's not going to change my number of protons, but it will, in fact, change my number of electrons to become 10. So those 10 remaining electrons are going to now feel an increased pull towards the nucleus because they don't have as many electrons to negate that charge. So what ends up happening, as we can see from this table, is that the radii decreases from 1.54, and these are in angstroms, to 0.97 angstroms. And then for chlorine, the opposite effect will happen because chlorine is one electron away from having a noble gas configuration. It has, I need to remind myself, 17 protons and 17 electrons in its neutral atom. But as we add an electron to chlorine, it now has 18. And due to electron-electron repulsion, that new electron that's going to be added is actually going to make the radius of this anion much greater than you probably would expect. So it starts off by being approximately 1 angstrom, and then it almost doubles in its radius. It goes to 1.81 angstroms. So the increase in the radius of an anion tends to be greater than the decrease in the radius of a cation. And we can see the same trend for all of these other anions and cations. So once we understand this effect, we don't need to spend too much time memorizing. We don't need to spend any time memorizing these. Okay, so let's look at practicing these trends for some species that are isoelectronic, meaning they have the same number of electrons. All right, so oxygen has 8 electrons, but when we add 2 electrons, it will have 10 electrons. Fluorine with 9 protons and 1 additional electron has 10. Sodium, 11 protons. Magnesium, 12. Each of those have 10 electrons once we remove 1 and 2 electrons respectively. Let's look at how the radius changes. Well, starting off, let's predict a trend. We might expect that the anions are going to have the largest radius. So oxygen and fluoride are going to be larger than sodium ion and magnesium ion. Okay, furthermore, oxygen has a double negative charge and magnesium has a double positive charge. So as we remove the electrons, the pull by the nucleus gets greater and greater. So although magnesium and sodium are in the third row of the periodic table and oxygen and fluorine only in the second row, that positive charge outweighs that greater shell number. In fact, there are no electrons anymore in the third shell. At that point, they actually have all the electrons that are in the, all these species have electrons that are only in the second shell of the periodic table. So let's write that out. Okay, so then what we'd expect here is that oxygen would be the largest and magnesium would be the smallest. Now let's go and look at the chart here. So magnesium 2 plus is 0.66. Sodium is 0.97. Fluoride is 1.33. And oxygen is 1.40. So in fact, predicting that trend is easy to do, and it matches to the experimental data. So that's a useful useful thing to know. All right, so I'm going to take a little bit of a break here now and explain how to name ionic compounds in more detail. We've already learned how to take the formula of an ionic compound and convert it into its name. But I haven't taught you how to take the name and convert it into a formula, nor have I taught you how to use the variable charge ions. So let's start off with something we're already familiar with, taking a formula and converting it into a name. But what we need to do is add in this extra element of some of these ions that form for metals aren't always going to be the same charge. Some of them are going to have a variable charge. To help you learn this, I recommend using the periodic chart of the ions handout and the method of charge crossing. So they look like this. So here's our periodic chart of the ions, and then here is our charge crossing technique. Additionally, you can go to this website. It's called ChemTeam, and they have a variety of tutorials and problem sets on chemical nomenclature. What we're specifically looking at are these two today. All right. Our textbook also has these two tables in Chapter 6. It lists all the metals that have one common ionic charge, which are our group 1 metals and our group 2 metals. So anything in the first group is always going to be +1, and everything in the second group will be +2. And then there are 6 other common ionic charges we should commit to memory. Silver always forms a +1 charge, cadmium and zinc 2+. Those are elements that are in the same group right here. And then let's put this up side by side. Aluminum is right here. So aluminum, zinc, cadmium, silver, scandium, and nickel. So nickel is here. Nickel always forms +2, and scandium always forms +3. So that's not too many to have to memorize. And then the groups that start with lithium, beryllium, those are always +1 and +2 respectively. Okay. Now, there are some metals that have 2 common ionic charges that are worth knowing, and these are the ones that are on the periodic chart of the ions. So if we go and look at this one, we can see gold, Au, has a +1 or a +3 charge. Copper is +1 or +2. Mercury is an interesting example that forms +1 or +2. However, when it forms a +1 ion, it forms a diatomic molecule. So it will be Hg2, 2+. I'll give an example of this in a moment. Lead forms +2 and +4 ions. Tin, +2 and +4. Cobalt is +2 and +3. Iron is +2 and +3. Thallium is variable charge, as is antimony and titanium. Titanium forms, interestingly, +3 and +4. There are a variety of other ones that I have listed on this table, but these are the ones that we're going to end up actually using the most. And then there are a few that are 3 common ions, and my chart doesn't include these, but chromium can be +2, +3, or +6, and manganese +2, +4, and +7. Cool. Now, why is this important? Well, because each of these charges changes the compound, and it changes its properties quite a bit. When we go to name these cations, we want to make sure that we specify which charge it is. So we'll write the charge using a Roman numeral immediately after the name in parentheses. And we can also use an older naming system where the smaller charge gets the suffix OUS and the larger charge gets the suffix IC. The reason I'm bringing this up is a lot of literature still uses this naming system, and I want you to at least be familiar with it if it ever were to come up. But all the problems I'll be asking for, I'm expecting you just use the modern naming system. Well, here are just some summaries of how we go from the chemical formula to the name. First, we need to know what the cation's name is. And we're going to look at the element and just write down its name. But if it's a transition metal, that's when we need to figure out what its variable charge is. One way to figure out the charge on the cation is to use these two rules. Take the charge of the anion and multiply it by its subscript, and then divide that result by the subscript on the cation. This will always give the positive charge on the cation. And then we need to name the anion. For single element names, we just take the root of that element and add the suffix IDE. If we're using the periodic chart of the ions, those suffixes are already applied on this table. So we can see nitride is IDE. Fluoride is, instead of fluorine, is fluoride, IDE. Some compounds will form from carbon, and they're called carbides, so that's not on here, but for the most part, we'll use these ones. And then we just combine those two names together to form the name of the compound. We don't want to specify the number of those ions because the name of the formula should already represent that, meaning we don't want to add any prefixes like tetra or tri. Those are reserved for covalent compounds, which we've learned a little bit of how to name already. So when we look at calcium and oxygen being combined, the cation for this one is going to be Ca2+ because calcium is in the second group. Oxygen is always going to be O2-. So the anions aren't listed there, but all of these ones are going to be 2- charges. All these anions are going to be 1- charges. And then all of these anions are going to be 3- charges. If you form something with carbon, it could be a 4- charge. But for the most part, again, we're just going to be making use of these ones here. All right, so what is the name of this? Well, since calcium is a fixed charge, we just write the name of that metal, calcium, and then we put a space, and then we name oxygen with replacing the ending part to IDE, and then this one doesn't have another name. Now, when we get to copper and chlorine, we need to know what the charge on the copper is. So let's start with the charge on the anion, which is Cl-. It's in the 17th group. It's 1 electron away from being a noble gas. And if we take the subscript here and multiply it by the charge on this anion, ignoring the negative charge, just thinking about it, so it's 1 times 1, and divide it by the subscript of the copper, that'll give us the fact that this must be a copper 1+ cation. An easier way to look at this one is just to say, well, if chlorine's -1, we need to have a positive 1 to balance it. The cations and the anions always need to cancel each other out. We have to have a net electrically neutral compound. And then the name for this would be copper 1 chloride. An old name for that would be cuprous chloride. Okay, this one should be straightforward to do now. We have iron, which is one of those variable charge ions. We can see that it can be either +2 or +3. Well, if chlorine is a negative charge, we have to have 3 negative charges to cancel out a positive 3 charge. So this has to be iron 3 plus, which comes out to be iron 3 chloride. And since in the antiquated name, we would give this the name of ferric chloride. Okay, example 4, I have the element tin and the element nitrogen. Well, nitrogen is going to have a 3 minus charge, and tin is variable charge. It can be either +2 or +4. Well, in this example, we can cross those subscripts to become the superscripts, because if this goes there and this goes here, we'll see that tin has to have a 4 plus charge. We need 3 4 plus charges, giving us a 12 plus charge, to cancel the 4 3 minus charges from the nitrogens. Do you see how that works? Hopefully you do. But basically what we're doing here is just taking those subscripts and trying to cross them to figure out what our superscripts are. And we'll do the opposite in just a minute. Well, this would become tin 4, and 4 is written in Roman numerals as IV nitride. The old name of this would be stannic nitride. All right, now this one is a tricky one. I put a mercury compound in here. We have oxygen 2 minus. Well, what does the cation got to be here? Well, mercury can have 2 different charges. It can be +1 or +2. When it is +1, this is a little bit misleading. It really should be Hg2 2+, because each of those mercury ions has a positive 1 charge, giving you a total of 2+. So when we look at this compound that results, oxygen normally has a 2 minus charge, and the 2 here, this subscript is referring to this diatomic molecule. So this is actually Hg2, mercury 1. Okay, so we would name this one mercury 1 oxide. Or mercurous oxide. Lastly, we have one of these variable charge metals that can have 3 possible options. Chromium. All right, so here what I'm going to do is we have Cr2S3. We know that sulfur has got to be a 2 minus charge because it's below, where did I go? It is below oxygen on the periodic table. So it's got a 2 minus charge. So we can take the subscript of sulfur, which is 3, multiply it by the charge on sulfur, which is 2. That gives us 6. And then we can divide by the subscript on the metal, which is 2, to find that this has to be a +3 charge. Or we could just simply cross the subscripts to become the superscripts. Okay. Whichever one of those works better for you. Chromium 3 sulfide. And this one doesn't have, I believe, an antiquated name because we'd have 3 different ways to write chromium. Okay, so let's go and practice this now where we write the formula from the name of an ionic compound. We're going to kind of do the same thing here. We just need to identify what ions that we have. And what we do need to do, though, in this case, is balance the charges. So we may need to take the superscripts, cross them to become the subscripts, and then at that point we may need to divide through by a common factor, such as 2. Make sure that you don't use a subscript for a single ion that's implied. We won't get to polyatomic ions until lesson, I believe, 14. Okay, so example here, I have sodium and oxygen coming together to form sodium oxide. So let's identify our cations. Sodium forms a +1 charge, oxygen a 2-. So the chemical formula here is going to be formed through doing this charge crossing. We're going to need 2 sodiums for every oxygen. And there we formed sodium oxide, Na2O. For aluminum and selenium, aluminum is a fixed charge of 3+. Selenium has a, well, you might not know where selenium is. Let's show you. Selenium is, oh, I got it wrong. Selenium is below sulfur. I don't know where it's at. It's a 2- charge. Of course, I made a hard one. So I got aluminum and selenium coming together. So in order to get an electrically neutral compound, we need to have 2 aluminums to get a 6+ charge and 3 seleniums to get a 6- charge. So we end up getting aluminum 2, selenium 3. I feel like these are a little bit easier, but maybe I'm wrong. Calcium, 2+ charge. Phosphide would be a phosphorus anion with a, let's take a look, with a 3- charge. It's below nitrogen. So here we're just going to cross these charges, giving us calcium 3, phosphorus 2. So maybe you want to practice these. You can pause the video at any time. I'll keep going. So iron 3 bromide. Well, the 3 here tells us this is a fixed charge metal. Iron must have a 3+ charge. Bromine is in the halogen column, so it's going to have a -1 charge. We'll get the compound iron with 3 bromines. And then, as you can see, I'm not writing any of the negative charges here or positive charges. It's implied when you write these formulas that they have positives and negative charges, as we've shown at the beginning of the lesson when we were writing the electron transfer equations out. Okay, so when we do this one, if we cross the charges, it would look like we form iron 2, oxygen 2. But that's not the right way to write this. We want to write this as iron oxide, iron 2 oxide, ferrous oxide. So we don't, we have to divide through by 2. Or you could just say, hey, for every 2+ charge, I have 1 2- charge. So that's a 1-to-1 ratio. Lead is given the symbol Pb. It's a 4+ cation. Iodide always is negative charge. So this would be PbI4. Silver. Silver is a fixed charge metal. We need to know that. It only forms this Ag+. Chlorine is going to be Cl-, so this would be AgCl. And then zinc is another fixed charge metal we need to know. It's got a 2+ charge. Nitride is a 3- nitrogen charge. So this one would be zinc. We need 3 zincs and we need 2 nitrogens. Wonderful. Okay, so we are approaching 50 minutes. This is a little bit longer of a lesson. I apologize for that. But you can always break these lessons up if you need a little bit more time to digest this information. You can go and practice some of these problems and come back. What I'm going to talk about next is the electronic configurations of transition metal ions. And this contrasts a little bit with what we were learning earlier. So when I looked at the order in which the orbitals were filled, I told you that we fill 4s before 3d, before 4p, just as if we are looking at the periodic table and we're filling up the orbitals in the order that they appear. So 4s, 3d, 4p. However, when we go to, apologize, give me 1 second. Oh, you got in? Okay. So let's see. So the only difference now for a transition metal ion is that this order doesn't stay the same anymore. So now we actually fill the orbitals in the numerical order. So 3s, 3p, 3d, 4s, 4p, 4d. Let's take a look at a couple of these examples. So if I have a chromium 2 plus ion, let's start with what the neutral chromium would look like. So chromium is here on the periodic table. It's element 24. Okay, so if it's element 24, that means it's going to have the same core charge, the core configuration of argon, and then we'll start here with the 4s electrons. So we'll say, we're just going to use the short notation now. So here is argon. That's 18 electrons. And then we have 6 left over. So for chromium, we'll do 1, 2, 3, 4, 5, and 6. Now, is chromium one of our exceptions? Let's look back at the last lesson, lesson 9. Scroll on to the bottom. Chromium is indeed an exception to the standard filling of the electron configurations. Now, why is it an exception? Well, it is 1 electron away from having a half-filled set of 3D subshells. So what can typically happen with chromium is one of these electrons will go into this orbital. So we'll write the proper notation for chromium, which is argon, 4s1, 3d, 5. Now, when we go to remove 2 electrons from chromium, because it can be of any of these, we change the order in which they're removed. So the filling order goes always into this order: 1s, 2s, 2p, 3s, 3p, 3d, then 4s. So what will happen here is we'll remove 2 electrons, and if I write it like this, we'll see that we should end up with 3d4 as our configuration for chromium 2+. And then for chromium 3+, we have to remove 3 electrons. So those would come from, we'd lose 2 of them from the 4s block, and then we'd remove 1 more from the 3d block. Giving us 3d3. And then chromium 6+ would remove those last 3 electrons to just give us argon. Okay, so this is why chromium has a lot of different properties, is because it can form a lot of these different ions. And even the neutral ion or neutral atom has an interesting exception going on here. Okay, so now sometimes ions can't lose all of their electrons, like chromium 6+, to get a full outer electron configuration. But what they can result in is a stable configuration called the 18 electron configuration. Two examples of this are silver and lead. So I'd like to do both of those with you. So let me take a minute to show you where silver is on the periodic table. It's element 47. Its electrons that are in the outermost shell are going to be in 5s and 4d. Silver is again one of our exceptions. So if we go back to lesson 9, we can see that silver is one electron from having a fully filled d subshell. So if we look at silver, we see it has a configuration of krypton 4d10 5s1. Okay. And then when we form the silver plus ion, we end up getting krypton 4d10. Why is this called the 18 electron rule? Well, we also have the 4s and the 4p electrons that are within the krypton core, and those are as a total 18 electrons. I can write this out in the long notation so you can see that clearly. And although it doesn't have a noble gas configuration, it does have a total of 18 electrons in its outermost shell. And that's somewhat of a stable configuration too. Transition metals are uniquely determined by the number of d electrons that they have. One other example of this is lead. And lead can form two different ions, 2+ and 4+. Let's start by writing out what lead's standard notation is. And I don't believe it is an exception. In fact, it's not. So lead is over here. It's got 82 protons, 82 electrons. It's going to have a xenon core. So we'll start there. And then we'll go to 6s. After filling up the 6s subshell, we need to fill up the 4f subshell, and then the 5d subshell. And then we can finally end with the 2 electrons that are left over in the 6p subshell. If we form the lead 2+ ion, what we're going to want to do is rearrange the order in which these are written. We'll start with the smallest number, 4f14, then 5d10, then 6s2, then 6p2. So what's going to actually occur is these 2 electrons are going to be removed first, and this will be our configuration for lead 2+. And then our configuration for lead 4+, we'll remove those last 2 electrons. And we'll end up with 4f14 5d10. When I go in to write this, sorry, I gotta fix this. This is 4+. For this one, I'm going to also write out the long form so you can clearly see the 18 electron rule. It's not readily apparent when you write it in the short form notation, but here we can see it: 5s2, 5p6, 5d10. Okay, now you're ready for inorganic chemistry. That's what some of the graduate students told me when I was teaching this. Okay, so last couple things in this lesson are about when we look at transition metal ions, predicting their magnetic properties. And we can predict what a magnetic property of a material is going to be by whether it has unpaired electrons in its outermost shells. And these materials that are characterized by unpaired electrons are known as paramagnetic materials. So let's start here. So paramagnetic materials have one or more unpaired electrons. These unpaired electrons will have an intrinsic magnetic moment due to their spin. And when we apply an external magnetic field, these moments will align with the field, making that material magnetically attractive. One example of a paramagnetic material is iron 3+. And iron has 26 protons. It's got the core of argon. So we can just get some practice here. So let's write iron by itself. So iron will have argon core, which is 18 electrons. And then we have a total of 26, right? So that would be 4s2. And then that leaves us with 4 left over. So we would have 3d6. For iron 3+, we need to change the order in which these are written. And, we'll remove the highest shell number first, so these get eliminated, and then this leaves us with 5. So 3d5. Making this a strongly paramagnetic material, because if I were to draw out each of these orbitals, there's 5 d orbitals. I can draw this evenly. There we go. There will be electrons that are spin up in each of these orbitals, which will align very strongly with any magnetic field that we have. An example of a material that's diamagnetic is going to be zinc 2+. So zinc is at the end of the first transition block. It's got 30 protons and a total of 12 non-core electrons. So let's start there. So 4s2, 3d10. When we write out zinc 2+, it's going to remove the 2 electrons from the 4s subshell, giving us argon 3d10. And when I go and I look at these orbitals, all of these electrons are paired up. So when we apply an external magnetic field, we're not going to expect that the magnetic moments are going to align. And this is going to be a material that weakly repulses an applied magnetic field. Okay, so paramagnetic, unpaired electrons, at least one. Diamagnetic, all unpaired electrons. All paired electrons. Now, the last thing I want to introduce in this chapter is Coulomb's law, and it's a way that we can calculate the energy of a ion pair. So we'll make use of this equation, which simplifies the math for us. There will be the introduction of this constant, 231, so that comes about from fundamental constants, but it simplifies the math in these problems. Q is the charge of whatever ions that we're dealing with. and d is the distance between the centers of these ions that we're looking at. So when I have two ions that come together, because they have opposite charges, they're attracted very strongly to each other. And this energy equation helps us understand how attracted they are to each other. If the charges have, instead of a positive 1 charge, positive 2 and a negative 2 charge, this energy attraction gets larger and larger. In fact, it increases much faster as we increase the charge on these ions. And I'll show you that in a minute. The distance is largely not going to be too variable. So what we'll do is we'll combine the radii of each of these charges together and approximate them as being touching spheres. Okay, so that's the assumption here. Here's some data that we're going to need to do these problems. Here I have crystallographic radii of the ions in picometers. And then I have both positive charged ions and negative charged ions. And then I have some successive ionization energies of the elements, and I have some electron affinities. So we'll make use of those as well, because what we'll want to ultimately do is figure out what the total energy of attraction is. But starting off with, let's assume that these ions are already ionized. What's the energy of attraction between sodium ion and fluoride ion? Well, what we'll need to know is what the radii of sodium is and of fluoride is. So sodium has a 102 picometer radii, and fluoride is 133. Okay, so if this, for example, is sodium and this one is chloride, we're going to say that this here is 102, and then here to here is 133. So the total of those is going to be 235 picometers. And the charge is going to be a positive 1 and a negative 1. And then all we need to do is use this equation. So the energy of attraction between sodium ion and fluoride ion is 231 picometers attojoules times positive 1 times negative 1 divided by 235 picometers. Oh. All right, so the energy of attraction here is negative 0.98 attojoules. All right, what about the same thing for beryllium and oxide? Beryllium has should be a smaller radius, I'm guessing. Beryllium, where is it? It's not listed here. Beryllium. Well, if we don't have the value, what we can do instead is, it's kind of weird. Barium. I feel like, did I mean barium? No, I meant beryllium. Okay. Oh, you know what? I have the value up here at the top. We can try this value here. So 0.96 angstroms. We'll just want to convert that to picometers. Okay. So 0.96 angstroms is the same thing as 96 picometers. And then oxide is going to be 140 picometers. The total of those two is going to be, it's a calculator on this one, 96 plus 140, or 236 picometers. It's actually the same. Like I said, the distances on these don't change all that much. The big difference here, though, is Q1 is positive 2, because beryllium's a 2 plus charge, and Q2 is going to be a negative 2 charge. So when we write this out, we're going to get a very different value. So 2 times 2 is 4 times negative 4, and then divide by 236, and we get negative 3.92 attojoules. The reason this is a negative charge, or a negative energy, meaning it means that these charges are attracted towards each other. So just by changing the charge to a plus 2 and a minus 2, we've increased the force of attraction fourfold. The last thing that we can do with Coulomb's law is combine it with ionization energies and electron affinities to estimate the energy that's gained in the formation of an ionic bond, starting with the neutral atoms in their gas state. So I'm not going to write the states of matter here, but assume these are ionized gaseous neutral atoms, and then they combine together to form this ionic compound, sodium hydride in this example. The positive and the negative charge here normally aren't included, but that's to help us see that they are in fact a positive and a negative charge here. For this problem, we're going to need to first convert the sodium atom into its ion. So step 1 is to ionize sodium to sodium plus and hydrogen to hydrogen minus. We can do this using the ionization energies and the electron affinities. So the electron affinities are listed here, and the ionization energies are listed here. So for sodium, we want to singly ionize it. So we're going to remove its first electron. It's going to be 0.83 attojoules. And then to add an electron onto hydrogen, that's actually a favorable process. So it doesn't require energy, actually results in the release of energy. It gives off negative 0.12 attojoules. Okay, so overall, we've done that process. Now we can combine those charges together. And we can figure out the energy of attraction through the Coulomb energy. Which I'll call a force. It's a Coulombic force that pulls them together. Now we got 231 as our proportionality constant. Q1 is plus 1. Q2 is negative 1. And then the distance between these, well, sodium plus has a 102 picometer distance, and hydrogen should be small. again, it's not, oh, there it is, 154. Oh, it's actually bigger than I expected because it is a negative charge. So 102 and 154. So that's going to be, I can do that math, 256. Okay, and then I need to multiply that by -1. So negative 0.90 attojoules. But the overall energy here is going to be the sum of all of these together. All right, so now we'll combine all these energies. So 0.83 attojoules minus 0.12 attojoules, so adding a negative, minus adding another negative, 0.902 attojoules. So what is the overall energy? Negative 0.192. And this is the energy per ion pair. And it's negative, showing that this is a favorable attraction of forming sodium hydride. Sometimes when you do this, you'll end up getting a positive value. And that's because we're not accounting for the lattice energy, which is the overall energy that's accounted for when we apply Coulomb's force to all of the neighboring ions. Because when we write out a sodium hydride interaction, there are other, there's other hydrogen ions and other sodium ions around this, right? And so if we account for all of those attractions, the Coulombic energy actually should get more negative. And anyways, that's just a small note there. Well, that's pretty much the end of this lesson. I do have a couple of other practice problems here. I will go through those if you want to spend the time here. So I'm going to go through these problems and do them. But feel free to end the video here. And if you choose to watch, then definitely keep on getting some practice here. So if we want to write the systematic name of AgBr, this is silver bromide. One thing I always do is I write the names of chemical compounds all with lowercase because these are not proper nouns. Silver is not a variable charge. It has a fixed charge of +1, so we don't write it as silver 1 bromide, although that wouldn't technically be incorrect. Lead can have two charges. It can be +2 or +4. In this case, since chlorine is -1, this has got to be a +2 lead 2 chloride. Oxygen is going to be 2-, and zinc is 2+, and it's a fixed charge. So this is zinc oxide. Copper can be +1 or +2. Since fluorine is -1, this has to be copper 2. Or we could write cupric fluoride. So copper 2 or cupric fluoride. Barium is a +2 ion. It's in the second group. Nitrogen's a -3 ion. It's in the 15th group. So we have barium, nitride. Okay. If we write the chemical formulas for some of these, we need to know that phosphorus forms a 3 minus anion. Let's do the rest of these. Chloride is -1, oxygen's 2 minus. And then all of these tell us what the charge is. So this is 3 plus, 4 plus, 4 plus, 6 plus, and 5 plus. So then what we're going to do on these ones is we're going to cross the superscripts to become subscripts. We have 3 and 3 here, but in this case, we need to divide through by the common factor of 3. So we just need 1 cobalt ion for every phosphorus anion to give us COP, or COP. And then titanium and chloride come together to form titanium and 4 chlorides. Magnesium, we need 2 oxygens to equal the charge on a magnesium 4 plus. So that gives us magnesium O2. Likewise, we need 3 oxygens to equal the charge on 1 chromium 6 plus ion. So this is CrO2. Oh, sorry, we need 3 of them, CrO3. And then for vanadium, here we need to have 2 vanadiums and 5 oxygens. So here we can just cross the charges to find V2O5. Using electron dot formulas to describe the formation of lithium nitride requires 3 lithiums and 1 nitrogen. So we'll start by writing out 3 lithiums. And I'm going to write it this way so that we can see how the nitrogen is going to pick up these 3 electrons. All right, so these electrons are going to go here, here, and here to fill up those 2 p orbitals. That's going to then give us nitrogen, 3 minus charge, and then 3 lithiums, the 1 plus charge. Are you starting work in a sec, Laura?
Yeah, in 60 seconds. I need to log on to the meeting.
All right, well, I'll finish this in a little bit, and then I'll combine the videos. Okay, and this next problem, we want to predict the ground state electronic configuration of tungsten when it's in the 3 plus state. My suggestion on doing these is to write them all as the neutral atom and then make the adjustment. So let's find tungsten on the periodic table. It's element 74. So in this one, we're going to need to make use of the 4F subblock because it's going to fit in right here. We'll start with the short form configuration. That would start with xenon as the noble gas core. That accounts for 54 of the 74 electrons. So we have 20 electrons left over. We'll start with the 6s subshell. 2 electrons will go in there. Then we need to put in 14 electrons in the 4f subshell. That gets rid of 16, leaving us with 4 electrons left over. We can see that really easily here, 1, 2, 3, 4, which means 5d4. But we want the ion configuration, so what we're going to do is we're going to rearrange these so that they're 4, 5, 6. And then we need to strip off 3 electrons. So those 3 electrons will first get stripped off from the 6s2 and then the 5d, leaving us with the configuration of xenon 4f14 5d3. The next question asks about isoelectronic cations and anions. This is cations and anions that have the same number of electrons. Let's start with the first example of lithium and fluorine. Lithium has 3 protons and fluorine has 9 protons. When we form the most common charges of lithium and fluorine, we'll get lithium plus, which will have 1 less electron, and fluorine minus, which will have 1 more electron. It should be quite obvious that in this case, we do not form a salt that has isoelectronic ions, because lithium will then have 2, it'll lose 1 electron, and fluorine will gain 1 to have 10. For them to be isoelectronic, they should have a noble gas configuration that's the same. So this one would not be the case. If we just look at this periodic table, sodium will want to lose 1 electron to become like neon. Since we kept the same anion, this one is composed of isoelectronic cations and anions. If we look at potassium and bromide, potassium here is going to lose 1 to have 18. Bromine will gain 1 to have 36. So that would not be one of these. And then, however, potassium and chlorine do have the same number of electrons in their ion forms. Barium, element 56, will typically lose 2 electrons to give us 54 electrons. Iodine, when it gains 1, will form 54 as well. So that is an isoelectronic salt. There are 2 iodines here, but I'm just looking at them having the same, each of the cations and the anions having the same number of electrons. And then this aluminum and fluorine, this one's an interesting one. So aluminum will lose 3 electrons, 1, 2, and 3, to be like neon. And then fluorine will gain 1 to be like neon as well. So here we have 4 different isoelectronic salts. With question 6, I want to place these ions in order of increasing radius. All of these ions are going to be isoelectronic. How do I know that? Well, if I take a look back at my periodic table, and we look at, whoops, where to go? Okay. All right, so sodium, it's going to lose 1 electron to have 10. Oxygen will gain 2 to have 10. Magnesium will lose 2 to have 10. Fluorine will gain 1 to have 10. And aluminum will lose 3 to have 10. So they're isoelectronic. So we can compare these with a simple knowledge that the anions are going to have the largest radius, because those extra electrons will overcome the nuclear charge and have some electron-electron repulsive effects, whereas the cations will lose their electrons in the outermost shell, and then the remaining electrons will be tightly attracted because the effective nuclear charge is much greater for those cations. They have more protons than electrons. So what we'll find is that the smallest radius will be aluminum 3 plus, and then magnesium 2 plus, sodium 1 plus, fluorine minus, oxygen 2 minus. The last question I have here is asking about the chemical formula Al2O7. Say, for example, we do an experiment and we end up getting the stoichiometric equivalency of 2 aluminums per 7 oxygens. This could be a correct chemical formula, depending on if the data suggests so. However, what are some ways we could argue against this being the correct formula? Well, first off, what is the typical charge for aluminum? It's typically 3 plus, and oxygen is typically 2 minus. So we would expect that a chemical compound formed from aluminum and oxygen would form Al2O3. That is one way to explain this. Another way to looking at this is to go the opposite way. What would the if I had Al2O7, do these charges cancel each other out? Well, 3 times 2 plus minus 7 times, I'll do it this way, 2 times 7, so the charge times the number of the atoms, gives us an overall charge of 6 minus 14, or negative 8. So this is not electrically neutral, which is a requirement for a compound. But that is why we need to be very precise when we do experiments and check our works with theory. Well, thank you for joining me for today. Next week, we'll talk about Lewis structures and valence shell electron pair repulsion theory. And if you want to do the extra lecture on valence bond theory and molecular orbital theory, that'll be available as well. Take care, everyone. Look forward to talking to you next week.